So in this problem, we have a space shuttle that is launching a satellite from an orbit of 6,700 kilometers to geosynchronous orbit. Now, at geosynchronous orbit, the period of the orbit is just 24 hours, or one complete day, which is the time it takes for the Earth to revolve completely once. So in part A, we're asked to find the radius of this geosynchronous orbit. So if the satellite is at geosynchronous orbit, then by Newton's second law, we have that net force is going to be equal to the force of gravity of the Earth on the satellite, which is going to be given by big G times the mass of the Earth times the mass of the satellite, which we'll call little m, divided by the radius of the geosynchronous orbit squared. And that is going to be equal to the mass times the radial acceleration, since in geosynchronous orbit the satellite is moving in circular motion. So that's going to be given by omega squared r. And note that omega is just 2 pi over the period of the orbit, so that's just equal to m times 2 pi over big T all squared times r. So now if we collect the radius terms and move everything else to one side, we get that the radius cubed is equal to big G times the mass of the Earth times the period over period squared over 4 pi squared. And notice that the mass of the satellite cancels out. So this means that the radius of the geosynchronous orbit is equal to big G times the mass of the Earth times the period squared over 4 pi squared. And that is all to the 1/3. So if we plug in our values for G, big G, which is 6.67 newtons times kilograms squared times meters to the -2, the period is 24 hours, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. So the radius of the geosynchronous orbit is going to be 42.2 megameters, which is 10 to the 6 meters, which is approximately 6.62 times bigger than the radius of the Earth. So in part B, we're asked to sketch the home and transfer orbit. So here we have the Earth. Alright, and the smaller circle is going to be our orbit of radius 6,700 kilometers, or 6.7 megameters. And let's say that this dot is going to be the location where the space shuttle first launches the satellite, and this larger circle is going to be orbit, the geosynchronous orbit of radius 42.2 megameters. Now, the home and transfer orbit is going to be an ellipse who's going to touch both the orbits and whose semi-major axis is going to be the average distance of the two orbital radii. So we're going to have an ellipse. It's going to travel like that. So that's our sketch of the home and transfer orbit. So now for part C of the problem, we're asked to find the time it'll take for the satellite to complete its transfer orbit. So that's just going to be half the period of the elliptical orbit that it travels in. So first let's calculate the length of the semi-major axis of its elliptical orbit. So let's call that A. So that's going to be the average of the two orbital radii which is going to be 6.7 megameters plus 42.2 megameters, all divided by 2, which comes out to be 24.5 megameters. Now notice that by Kepler's third law, we have that the period squared is going to be proportional to the semi-major axis cubed, which means that the period is proportional to the semi-major axis to the 3/2. Now this means that the time it'll take is going to be half the period, which we'll call big T, naught, and the period is just going to be, well, it's going to be the period of the outer radius, or the outer orbit, which is going to be 24 hours, times, well, we know that the ratio of the semi-major axis of the elliptical orbit to the outer orbit is given by 24.5 megameters over 42.2 megameters. So that's how much smaller the semi-major axis of the ellipse is compared to the outer orbit. And since the period is proportional to the semi-major axis to the 3/2, this means that the period is smaller by a factor of 24.5 megameters over 42.2 megameters to the 3/2. So if we solve that all out, we get that the time it'll take for the satellite to complete its transfer orbit is going to be 5.3 hours.